This video will be about enthalpy calculations. So these are your four primary formulas for calculating the change in enthalpy, where delta H means the change in enthalpy. We could calculate the change in enthalpy, but we cannot calculate the exact value of enthalpy within a reaction. So these formulas are pretty self-explanatory, where we calculate delta H. Another thing that you need to know is that the change of enthalpy is measured in kilojoules per mole. This equation to solve for delta H goes hand in hand with another equation where in order to solve the change in enthalpy, we need Q. And Q is just the energy released. Q is measured in joules. And it's important when we calculate delta H, because it's measured in kilojoules, we must convert these joules into kilojoules. Firstly, before we go to practice questions using these formulas, let's go through the formula for calculating Q. So firstly, Q is just energy released. M is the mass of the substance it's in. Most of the time it's water, and it's measured in kilograms. C is the heat capacity of the solution. For water, it's 4.18 times 10 to the power of 3. And delta T is just change in temperature. When calculating delta T, it's important that we don't need to convert Celsius into kelvins. For example, if we want to calculate the change of temperature from 25 degrees Celsius to 30 degrees Celsius, it will be just 5 degrees Celsius in difference, right? But let's say we convert Celsius into kelvins. We put this into the calculator. It will give us these values in kelvins. Now let's calculate the change of these, which is 303.15 minus 298.15, which would give us a difference of 5 kelvins. And as you can see, they have the same magnitude in difference. So we don't need to waste time converting Celsius to kelvins, only when calculating for Q. Now let's use these formulas in questions. So this is a past paper of Sydney Grammar in 2023. Question 22. Two students, John and Marrett, were asked to determine the value for enthalpy of combustion of methanol. And we have a table of average bond enthalpies for bonds of the reactants and products. So firstly, in order to know what bonds we need to use, we got to draw out the structure of this equation. So we know carbon has 4 bonds, and there's 3 hydrogens near it, and there's oxygen, and there's another hydrogen. So that's methanol. Plus oxygen, oxygen gas, and these reactants give us CO2 plus 2H2O. And also, it's important that we keep in mind of these coefficients here because we need them for our calculations. So that's 1.5 of oxygen gas, and there's 2 H2Os. So now we know the bonds in all of our reagents. Now we could use our formula where delta H equals bonds broken minus bonds formed. So we can see here, these reactants must break their bonds in order to form new bonds with their products. So first we must calculate the enthalpy of bonds broken. So there are 3 hydrogen to carbon, and we can see here the bond enthalpy value of these bonds are 413 kilojoules per mole. So we got 3 C to H bonds. We also got carbon to oxygen, and that's this value right here. And we only got one of them. We also got oxygen to hydrogen, which is right here, and we only got one of them as well. And our last reactant is oxygen to oxygen, and it has a double bond, which is oxygen to oxygen with a double bond, which is 495. Now we have the delta H of bonds broken, and now we minus that with the delta H of bonds formed. And one thing, oxygen to oxygen has a coefficient of 1.5, right? So we got to take into consideration of its coefficient. So we got to times their bond enthalpy by 1.5. Now we got to calculate the enthalpy of the products or the bonds formed. So we got 2 C to O's that are double bonded right here. And we got 2 of them. plus, we also got to take into consideration of the coefficient. And we got two hydrogen to oxygens. And now this should give us our delta H of the whole reactant, the enthalpy of combustion, which if we put into the calculator, gives us minus 657.5 kilojoules per mole. That was question 22. Which we got right. So we've already used this formula in action. Question 22b of the past paper. Laura placed the beaker containing 100 ml of water above a spirit burner containing methanol. She weighed the spirit burner and measured the initial temperatures of water, lit the spirit burner and waited until the temperature had increased. Weighed the spirit burner again, measured the final temperature of water, and placed her results. So we got to calculate the enthalpy of combustion using Maurits's results of calorimetry. So we want to calculate delta H. The formula for it is minus Q over N, which is energy released over moles. To calculate the amount of moles, we first need to find out the amount of methanol used, the mass of methanol used, which we could just figure out by minusing the initial and final masses. Initial and final. So the total amount of methanol burnt is 0.282 grams. With the mass of methanol used, now we could calculate the moles, which is our first step in calculating delta H. We know the formula for getting our moles is moles equals mass over mole mass. This is the amount of moles used. Now we've got our amount of moles, now we need to calculate our Q. So over here, Q equals MCAT. We know the mass of water used, 0.1 kilos. We know the heat capacity of water is 4.18 times 10 to the power of 3. And our delta T, change in temperature, is the final temperature minus initial temperature. Which when we put it to our calculator, gives us 4,305.4 joules. And since delta H is calculated in kilojoules, we must convert this value into kilojoules as well. And we know 1000 joules is 1 kilojoule. So this amount of joules is just 4.3054 kilojoules. So now we got our Q value and our N value. Now I could easily calculate delta H minus, which gives us 489.1. We also got to round it to significant figures. Round it to 3 significant figures. Which gives us minus 489 kilojoules per mole. Question B of 22. We should got 489. It says 0.25, which we didn't get because their results, they rounded the moles into 0.0088, which I recommend not to round your values until your final calculation. So now we've used these formulas in this formula. Now our final formula is products minus reactants, which is one of the easiest formulas. So let's say, consider this equation. where we know the delta H of formation of NH3 So we're going to calculate the change in enthalpy of this reaction. The question gives us the delta H of formation of each reactants and products. So we know the delta H of our reaction equals the products minus reactants, which is this minus this. Delta H formation of NH4Cl is just minus 315.5. And we minus it by our reactants. Which when we do, gives us minus 268.8 kilojoules per mole. Wait, I happened to the calculator wrong. Which gives us 177.6 kilojoules per mole. And that's how you calculate delta H, knowing the delta H for formation of products and reactants. So these are the formulas you need to know for calculating enthalpy.